All right, let's take a look at our lesson for today. We are going to be looking at exponential models. So in other words, I know our favorite word problems. I know we don't like word problems generally. So this kind is really mostly to do with exponential growth or decay. And so that's the topic that we do in AB calculus for the most part, exponential growth or decay. And there are two formulas associated with that. So first of all, let me go back to exponential growth. So this is where we assume, well, the rate of increase or decrease of a population at any time is directly proportional to the population. This is the key word right here, this directly proportional. Okay, so directly proportional, perhaps you remember maybe from like Algebra 1, remember back in the day when you were talked about direct proportionality and inverse proportionality, you remember all that? Or like, no way, that's been too long. Okay, so I'm just going to remind you, directly proportional, when we learned it, back in the day, if we were directly proportional, the variables, in most cases, x and y, but it could have been different things, are directly across from each other. This is direct. This is directly proportional. Do you remember the k at all from that business? Maybe, maybe not. So we're going to have k's here. Inversely proportional was like this. That was inverse. Ringing any bells yet? No? Okay, so, and then we had jointly proportional. Oh, yeah. Remember that one, which would be like, I don't know, it would have been like two things multiplying, like x times z or something. This is jointly proportional. So these concepts are what we're building off of with exponential models. And many of the ones that we're going to do have direct proportionality. They're directly proportional. And actually this is the, and these are formulas we have to memorize. I know you're really excited about that. So this one that I'm highlighting right here, this is the differential equation. This is the differential equation that goes with exponential growth and decay. And so this is where you see the direct proportionality. You see that the rate, which is like dp dt, is directly proportional. The rate of the population is directly proportional to the population. It would be like, that's directly proportional. And attached to that is our solution. Now, this is a vocab word. Do we remember what the solution is? The solution to a differential equation is what? Is the position. The solution to the differential equation is the position. And this is the general solution, or it's the position. So this is the position for our exponential growth and decay. Okay, so that's some important background information that we need to understand before we go and jump into this and convert stuff from words to symbols. Is everybody okay with that? Okay, so we're building off of these old topics of direct proportionality, inverse proportionality, and we have this k. Okay, k is going to appear in all of our stuff, or we're going to know what it is. I mean, it's going to be there. K is going to be there. If you don't put a k, then you're saying that k is 1, which we really can't just assume that k is 1. Okay, so we have to put that k in there. So the first couple of questions, let's look at these. They're just asking us to set up the differential equation for each scenario and then solve using separation of variables, which we have done before. That's a lesson we've done before. So let's work on the first one. So the weight of an animal is increasing at a rate proportional to its weight. The weight of an animal is increasing. Okay, what does this mean? This means this is a rate, right? The weight of an animal is increasing. This is a rate. So dw dt, and we're talking about with respect to time with this kind of applications, where it will be with respect to time. So the weight of the animal is increasing at a rate, so dw dt, proportional to its weight. So that's direct proportionality, proportional to its weight. Okay? So we're going to separate, like we did the previous lesson, we're going to separate these and do the antiderivatives. So the dw, we would divide by w, and we'd have k dt. We're going to integrate both sides. We have ln absolute value w equals kt plus c. We need to solve for w. We are supposed to solve for this, whatever this variable is, we have to solve for it on our differential equations. So remember how we get that out of the argument of the logarithm? Remember that? The natural log, how we do e to that side. So e to the kt plus c equals w. Okay, this is the general solution. Now, as I write this, I'm going to write down this. I want us to think about this for just a second. That's our formula for the position, and I'm going to write this underneath it. Okay. So this is very, very close to what we're looking for. All we are lacking is this, right? We don't know P naught, which is the initial condition. And we also haven't found C. Okay, are we okay so far? Okay, so we haven't found C yet. We don't know the initial condition, but in future problems we will. We'll have an actual equation that we can use. All right, so let's look at one more. We're going to set one more up. This one is a bacteria population is shrinking at a rate proportional to its population. So see, bacteria population is shrinking. So that's my rate, right? So, and it's a population, so we'll call it dp dt equals proportional to its size. So the proportional to the population, so k times p. This is exactly the same even variables that they use on our differential equation. So let's separate. So I have dp over p equals k dt. I'm going to integrate both sides. So I have ln absolute value p equals kt plus c. Does everybody understand where the kt comes from? Why did I put a t by the k? Because it's the antiderivative. Like that would be like a 2, right? K is just some kind of number, maybe 2. If it said 2 dt, then my antiderivative would be 2t, right? That's the way that works. So now we're going to convert. So e to the kt plus c equals p. Again, we are, and I'm not going to set it up, but we are very, very close to the actual position. Okay, we can look at that. We can see it's basically the same thing. We're just missing our initial condition, and we don't know what C is.
So since it's increasing this decreasing, would that just mean that like if you actually have numbers, it would just be regular?
That's right. That's right. If we had numbers, then the numbers would add meaning to this equation, and we would be able to tell that it's increasing and decreasing with the numbers, if that makes sense. Yeah. Okay, so let us look at our next slide. So here, we're going to find the particular solution for each differential equation. And this is just what we did the other day, but these are special. I want to show you these because I want to write this over to the side. These equations are in the form of dp over dt equals kp. So we can go straight to the solution slash, which means position. I'm going to say that one more time. So these equations are in the form of this dp over dt equals kp. So we can go straight to the position or solution. We do not have to do the antiderivative and go forward. Now you can if you want to. You'll just get to the same place that we're getting ready to go, just a little bit slower. But you totally can if you want to. But I'm going to show you how to navigate through this and go straight to the position. Okay, so everybody okay so far? Okay, so we are going to go, we're just going to use the information and we're going to translate it into the position. So I'm going to write down both of those formulas that we'll need to memorize. So we've got the dp over dt equals k times p. And we've got the p equals p naught e to the kt. Those are the formulas that we have. So let's take this and let's match this information up right here. So what I'm working on is I'm working on these things right here. I'm matching those parts up, right? So instead of using a p here, we were going to use a y. Y'all see that? So instead of using the variable p, we're going to use the variable y. That's fine, not a problem. And notice what k is. They tell us, I mean, it's right there. K is 6. I mean, that's what it is. Okay, so that's so far. So I'm comparing differential equations to differential equations. Everybody understand what variable we're using and what k is. That's what we get out of it. What variable we're using and what k is. This portion right here is the initial condition. So do we understand, what does initial condition mean? What does that word mean? Is that a special kind of a condition? Isn't that the very first condition, right? When t is 0, it's our beginning situation. So they're saying that's our initial condition. Okay, so the initial condition is going to go right here, right where that p naught is. That's where the initial condition is going to go. And this k, I'll just highlight this k right here, is going to go here. And of course, instead of using p, I'm going to use y. Okay, so let's write that. So I'm going to this position, so I have y equals, and my initial condition is what? What's y initially?
5.
It's 5. And what is k? And I can read k out of the differential equation. What is k? It is 6. And that's my answer. Now, if you want me to, I can show you how we would get there without doing this. Would y'all? I'm just on this first one. I'm just going to show you how we can get there. If let's say you don't even recognize that's what's going on, what would you do? So this is the way that would be faster, but what if we don't recognize it? What would we do? So we would separate that. We'd have dy over y equals 6 dt. We integrate both sides. We'd have ln absolute value y equals 6t plus c. The very first thing that we do when we get c is we plug in our initial condition. So I have ln of 5 equals 6 times 0 plus c. So c is ln 5. So I have ln absolute value y equals 6t plus ln 5. Okay, once I get there, what do? I solve for y, right? I convert it. So e to the 6t plus ln 5 equals y. Okay, do we remember the scenario about this piece right here? Remember how we simplified that last time? Are y'all like, no, I've slept since then? Remember how, like, if I'm doing, this is just scratch work, okay? If I have, like, x squared times x cubed, what do? Don't I add those together? Right? Isn't that x to the 2 plus 3? With me? Same base, add. Here I'm adding and I go backwards. This would be like e to the 6t times e to the ln 5. And this simplifies. Y'all remember e to the ln 5? What happens to that? It collapses to be a 5. So I basically have y equals 5e to the 6t, which is exactly the same thing that I had using the formula. Okay, are we all okay? So it's okay if you don't know how to use the formula like that. If it freaks you out, it's okay. You can just do it regular. Just go ahead and separate and integrate. Okay, one more like this, and I'm going to use the formula if that's all right. I'm not going to do this second way. All right, so let's use the formula. Okay, so let's identify what we've got going on over here. So this is, what is this? What does this represent? K, that's K. And then this part right here is our initial condition. Okay, so I'm going to write down our position. So P equals P naught e to the KT. That's the formula that we're subbing into. Now, am I going to use P's on this one? No, I'm going to use Y's, right? Aren't they using Y's? Yeah, they're using Y's. Okay, so I'm going to have Y equals, what's my initial Y value? 4 e to the, and we just said that K is negative 3. And that's my position. Okay? Okay, how are we doing? Now we're going to get into some word problems where we're going to practice this stuff. So we're kind of easing into it. We talked about the two formulas. We've talked about the position formula and the differential equation formula. And we've talked about how we can go straight to the position to save us some time. Okay? So now let's look at our, we have two word problems. All right, here we go. So let's read through this. So an animal weighs 3 pounds at birth. What did they just give us? What does 3 pounds at birth mean? Initial condition. I'm just going to circle it and I'm going to write initial condition just to help me when I read through this. I would suggest you do some kind of thing like that too. That's my initial condition. And 4 pounds just 3 months later. This is an additional point that apparently we need. This is an additional point. I don't know, must need it. The weight of the animal is increasing at a rate proportional to its weight. Doesn't that sound crazy? Weight proportional to weight? Well, that just tells us this is exponential growth. The weight of the animal is increasing at a rate proportional to its weight. So the rate dw dt equals kw. The rate that the weight is increasing is proportional to the weight. Now, in this case, I would love to go to the initial condition. I actually am going to go to the initial condition, but we are missing one thing. We have our initial condition, but what do we not know? We don't know K. Okay, so we don't know K. So we need an additional point to find K. We need an additional point to find K. Okay, so I would love to have K, but I don't. So what do? So here we go. So I'm going to go to the position. So the position would be W equals, we have our initial, right? 3e to the kt. So we did pretty good, actually. We're almost there. We just don't know what k is. Okay, so what am I going to do? I want to move this up a little bit. I'm going to find k by using my additional point. Okay, we're going to use our additional point. So the animal weighs 4 pounds. 4 pounds, 3 months later, 3e to the k times 3. Okay, so we got the time, which is 3 months, and we have the weight, which is 4. And now we're going to solve for k. And this is just some pre-cal stuff you may or may not remember. So we divide by 3. We got e to the 3k. Remember the circly thing? How do we solve for k? You could ln both sides, or you could do the circly thing, whichever one you prefer. So I basically have ln of 4/3 equals 3k, because ln of e wipes it out. So k is going to be 1/3 ln to 4/3. Now here's my suggestion to you. Once you find k, you should box it in. That's k. Now when we write, this is our formula right here, right? I'm going to say that k is 1/3 ln 4/3, so I don't have to keep writing that over and over again. I'm boxing it so that now every time I write k, it's going to mean 1/3 ln 4/3. So let's make ourselves a note. So we circle k, bless you, so that we can use k in future work on this problem and not have to write 1/3 ln 4/3 over and over again. So this is a time saver. You do not have to do this. You can totally write, for k, you can write 1/3 ln 4/3. Okay, and we want to put it in our calculator. So this is a calculator problem. So we would store it in our calculator. Are y'all good with storing numbers in the calculator? Y'all are good with that, right? So we would store in our calc. Okay, because they're going to want us to do something with this. That's why we went through all of this. The word problems typically ask us to find something. And in this case, they want to know how much will the animal weigh when it's 5 months old. Okay, so we want W of 5. And W of 5 would be 3e, and the k is this one we've stored in our calculator, times 5. And we would simply put that in our calculator, and it would tell us. So W of 5 is 4.845, and our units are pounds, right? Pounds. And so that would be our final answer. So we box in k. What's it?
Like on the one that has the answer.
Oh, this W of 5. That should be, sorry, that's a messy 5. W of 5 equals 4.845 pounds. Okay, so that's the kind of word problem that we will encounter. How are we feeling about that one? Is that okay? Okay. Okay, one more question. So question number 6 says a population y grows according to the equation dy dt equals ky, where k is a constant, t is measured in years. Okay. If the population doubles every 7 years, what is the value of k? Okay, now they didn't give us our initial condition, did they? But they did give us some information. All right, so let's write down our formula. So y would equal, we'll write a c, or y naught. C So C is the same thing as y naught. It's the initial condition for y. E to the kt. And we don't really know, well, what do we not know? We don't know our initial condition, but we do know this situation. If the population doubles every 7 years, what is k? Okay, so really, you could make the initial condition anything as long as you double the number, right? What if I made the initial condition 1? What would my result be? It would be 2, right? If I made my initial condition 2, what would the result be? 4, right? If I made it 3, it would be 6. You know, it doesn't matter. E to the k times, and that's t is 7. Okay, so this, as long as this proportion matches this doubling business right here, we're fine. As long as whatever your initial condition is doubles, we are perfectly fine. So it wants us to solve for k, so let's do that. So we would ln both sides, so ln of 2 equals 7k. So k is going to be 1/7 ln 2. And that's it. I highly encourage you to solve the equations like that and this is the exact k. When you put that in your calculator, you're going to have a decimal approximation. So it's nicer to have the exact value, if that makes sense. All right.